Hello everybody, my name is Jack Soh. I'm an associate professor in antenna design and technologies with the Center of Wireless Communication, University of Oulu, and 6G Flagship. And today I will be talking about antenna technologies for future communications. This is the outline of my presentation. First, I will introduce the challenges in 6G for antennas and what are the visions and motivation for us to research and to do what we do. We'll also talk about reconfigurability of antennas and apertures before summarizing today's talk and acknowledging some of our team members and sponsors. First, I will introduce what is interesting about antennas in the next generation communication, and I will describe to you about some vision and motivation. I will also talk about reconfigurability of antenna apertures before I summarize and end with some acknowledgement for today. I am imagining myself in the year 2030. I am aging faster than I should, so I would be 75 years old, and I would be fitted with all kinds of wearable sensors or implantable sensors on body, and being fully retired and probably not so healthy, I would be traveling between healthcare facility and on the streets and in my home. And what do I expect in this year 2030 with 6G is that I would like to have my parameters and my communication sensed in a very intelligent way. And I would imagine there would be many of these antennas and reflectors that are reconfigurable and operates in different frequencies that will be able to sense and communicate effectively in a smart electromagnetic environment. Let's have a look at how many antennas do we have actually in our current devices. So from the breakdown of this phone, you can see that there are so many antennas in a very small device, and things will be getting smaller and will be getting more challenging. And the typical way is that we would like to operate one or several wireless standards using a single device, and more antennas would be fitted inside this device. Or we could think of how is a better way to do this, considering that in WRC 23, we have several more study bands that are being defined for future wireless communications. So as you can imagine, there have been a lot of radios and antennas integrated in many of our everyday devices, and including things that we can see around us. And sooner or later, we will be integrating sensors and antennas and radios onto, and around our bodies. And will it be something like this in the near future? That remains to be seen. Let me take you down memory lane from a work which I have the privilege to supervise a group of very brilliant students in Leuven. And what we thought about this at that time was to try to integrate antennas and a radio and a smart system which collects biotelemetry signals from a body which we visualize as this cylinder here. And we fill it with tissue simulating liquid, and we test it with interference and intended signals. And in summary, what we found is that to enable such smart wearable systems, we need to think of how to make such system switchable or reconfigurable, controllable or programmable, and also smart and intelligent. Of course, the definition of smart antennas 10 years ago wasn't the same as you would imagine today with the development of AI. Probably just to also introduce where antenna stands in the whole 6G picture, I have tried to answer this question first, and the most common question that I have is, what is 6G? And my brief answer would be, it's a lot of things, but what antenna is relevant with in the flagship is these two areas, which is about devices and circuit technologies, and also probably one of the many applications that we have defined within the 6G flagship. Now let's proceed to the next section about the reconfigurability of antenna apertures. So as we know, antennas can be reconfigured in many ways. We can do it in terms of beam, frequency, polarization, or in any combination of the above. And as you can see on this graph on the right, different technologies operates in different frequencies, but a brief summary of all the broad approaches that we can use for antenna reconfiguration is either mechanical, semiconductor switches, or tunable materials. And in 6G, we started to look at the sub-terahertz band, that is between 100 and 330 gigahertz. And the main reason that we choose this is the availability of a large bandwidth. But what we found is these challenges, which is interesting for, of course, researchers. And of course, we took it as the challenge. We know that with the propagation in these bands, we know that we will have very limited range. We have very narrow beams that are generated, and that affects the coverage. And also, there are very limited material choices, which are not well characterized, fabrication technologies, which are not really well developed as well. And most importantly, there are very limited tuning technologies available, as you have seen in the previous slide. And due to the limited range and coverage, what we would need in antennas and reflectors are those three. We would need a very high gain to overcome this limited range. And at least we would require some reconfigurability in terms of beams so that we can point the already narrow beams towards our intended destination. And with so many possible targets that needs to be covered, we will need intelligence to be able to reconfigure these antennas to the correct direction in a suitable speed. To answer these questions, we did a very comprehensive review paper, which is published recently. And we compared about what antenna types there are, what kind of operating frequency, and to help us with finding potential additional antennas that are suitable for this kind of frequency, we extended this study a little bit lower in the upper millimeter wave bands besides the sub-terahertz. And we also looked at the aperture sizes and what kind of peak gain and what kind of fabrication technology that has been used. So we can summarize that there are arrays, there are leaky wave antennas, lenses, and also the combination of them. And going further, there are even more smaller numbers of demonstrated reconfigurable surfaces. And we can summarize that they are either transmissive or reflective. And we notice that most of them are passive, and they are fabricated using very specialized processes and have limited beam steering angles and efficiency. Realizing the potential of lenses and the potential integration of it with silicon, we started our investigation on reconfigurable antennas in the sub-terahertz band with the silicon lenses and on-chip antennas at 300 gigahertz. In this study, we linearly fed a 1x4 feed array with different feeding scenario, and then we did the fabrication of this lens and on-chip antenna, which is measured using a power detector at 300 gigahertz. And we also tested the beam steering capability, mechanical, for this silicon lens, which is very small. And we noticed that after characterizing the radiation pattern and link distance, beam steering can be achieved by up to plus minus 30 degrees, and only by tuning this in very small sub-millimeter steps. And maybe back to what I have talked about from 10 years ago, I have also started to think about how we could reconfigure these antennas, which is quite simple here, to be more reconfigurable in terms of beam steering and frequency. So one of the questions I asked myself is that could liquid metal be an answer? And we fabricated this simple structure on the right, which doesn't move, but it includes liquid metal inside PDMS structures. And we noticed that the antenna performs with more or less similarly with the conventional antenna that is not shown here. And why did we think about this is that you can imagine when we use liquid metal, we can reconfigure the antenna structurally in a non-toxic way, as these liquids are non-toxic, and it has very favorable properties for use in antennas. So imagine that if you have the printed circuit board, and once it is printed, then we won't have any ways to change that. But if we try to include liquid metal in substrates, then probably we would be having more flexibility. We started looking at one of the works in 300 gigahertz, which was published here, and which uses transistor switches. As you may see, this is a unit cell of a metasurface, and it has very small dimensions and 8 switches on one unit cell. And what they did was that they could be changing the length of the unit cell and adjusting the amplitude and phase response of this unit cell. And also we found that we can do this in an equivalent way using microfluidics, and this is much lower in frequency. And this is by actuating this input and producing this gap that will change and emulate the phase and amplitude response that we need. And this is what we are currently developing with our collaborators in the MIC research unit. What we are trying to do is to pump liquid metal in these unit cells in both ways. And hopefully by doing that, we will be able to gather sufficient phase changes for such reflective surfaces, and before integrating with programmable network. And as you can imagine from the previous slide, we have also emulating the same way as the electronic work. We took more fundamental approach before we started with the microfluidics structure. So we try to think of how we can actually code the reflectors with the phase changes that we need. So as you can see here, our simulations has produced the required phase response with the 90-degree phase changes and very small amplitude changes. And this is paper published in UCAP. And as you can see on the left, different sizes of the liquid metal contained in unit cell will produce different phase response and are coded as 0, 1, 2, and 3 to form a 2-bit digitally coded reflector. And we designed this reflector to be operating in 140 gigahertz, which is in the D band. And we designed it fixed so that we can reflect it towards these two angles, 6.9 and 10.4. And we tested it manually in our lab for half a meter away from these surfaces. And we noticed that we have 60% measured reflection efficiency, and we have simulated error versus measured of less than 2 degrees. However, we realized that this kind of measurement error are not satisfactory, and we have worked with our measurement team in the RF group to develop this in-house automated measurement system. And from this system, we have able to achieve better measurement accuracies, which enable us to characterize such reflectors in a more accurate way. And using this new system, we have found that the angles can be measured in a better way. And as you can see, the lines are pretty smooth with the increased angle resolution that we can get from this very basic study. And also, if you can see on the graph, we compared the received reflected power from these reflectors with copper and without reflector. And you can see that the increase in the received power is pretty significant. And how do we move further back thinking about the liquid actuated structures? So you can see that we are thinking of a very simple way of actuating the size change. Of course, this is a different shape from what we have done before. And what we do here is we try to push this elastic film that is integrated at the bottom of this unit cell so that we can change the size of the unit cell and, of course, consequently change the phase. And the overall reflector resulting from this unit cell is shown on the right. And you can see that it can be designed in the same way and coded digitally so that it can produce the required scanning angle that is needed for a reflector. So one of the more recent questions we ask ourselves is, can the reconfigurability of antennas be done without additional circuits or actuators or power? And this is what we are trying to do in a fellowship awarded by the Research Council of Finland, where we think of an antenna that has been integrated in an ingestible capsule. And we try to think about published work of an antenna which is operating according to this magnetoelectric resonance principle. And from this principle, the antenna can be miniaturized as small as 1/1000 of its wavelength without performance degradation. And the next challenge is, how do we do a passive pattern reconfigurable antenna without incurring any power or additional circuits? And what we are thinking here is rather challenging, is using this gravitational mechanism that we have naturally in the environment. And when the ingestible pill travels down the inside of the body, can it be tumbling and turning according to what we want on the outside of the body to sense and to receive signal in the correct direction? And this is an overview of this gravitational mechanism, where we are able to redirect patterns according to the content of the liquid inside this case, and for the broadside and also a little bit towards the right. And we have done some initial simulations of a liquid flow in COMSOL, combining the red, which is sodium hydroxide, and also the blue part, which is the liquid metal. And you can see from this graph, these shots, that many orientations can result in the effective movement that can be potentially further integrated with the small antennas that may be placed on the outside. But yes, let's summarize this talk. What are the future directions of antennas in future communication system? What is required is on the left. What are the challenges are on the left, and what may be the solution are on the right. And we can see that there will be more and more wireless standards that needs to be covered with a single device or single antenna using minimum structures and sizes. And then we see that there is a need, especially in the Sub-Terahertz, that we need reconfiguration in terms of beams and in terms of frequency tuning. And finally, the joint use of the communication system together with other applications such as energy harvesting and sensing. And of course, we are not working on those topics alone. We have a rather broad range of antenna topics that is being investigated currently in our group, besides the Sub-Terahertz antenna and reflectors. And several examples include base stations, wideband and multiband antennas for them, and how we can mitigate coupling and matching and interfacing to the radio front end in those applications. And of course, we have as well more compact antennas, which are designed using conventional principles. And we are also working on trying to make our passive reconfigurable surfaces active with amplifiers. And finally, I would like to also acknowledge my team members and our sponsors, national and international, who have been supporting our work so far. And probably several news as well about our articles, which has been quite popular recently in 23, and also several awards and scholarship that has been awarded to our team members. That concludes my presentation for today, and if you have any suggestions, comments or questions, please feel free to contact me. Thank you.